JJ Thomson, one of the scientists back in the late 1800s, realised by using these forces, the electric force and the magnetic force, you could actually work out what the mass ratio of was electrons to mass. You could set up this experiment and calculate that. So this is one of the landmark experiments in modern physics at the turn of the century, the measurement of the charge to mass ratio of an electron, E over m. This quantity was first measured in 1897. The discovery that this ratio is constant provided the best experimental evidence available at the time of the existence of electrons. So this proved basically that there was a fundamental particle with definite mass and charge. His experiment offers an important and interesting example of magnetic field forces. Thomson's apparatus, shown here, is very similar in principle to the cathode ray tube. Electrons from the hot cathode C, so this is the cathode here. Basically, you put a voltage across it, and such a high voltage that electrons just boil off it. They're vibrating so much due to the high voltage that some of them escape this plate. They're formed into a beam basically by these anodes here, A and A dash. So this beam is accelerated through these two anodes and goes through between these plates P and P. After passing between the plates, the electrons strike the end of the tube, so they go over here and they strike the tube, where they cause fluorescence material at S to glow. The speed of the electrons depends on the accelerating potential V. The kinetic energy, a half mv squared, equals the loss of potential energy, EV, where E is the magnitude of electron charge. So EV here, remember that that's basically potential energy, you know, because voltage is joules per unit charge. So if you multiply it by the charge, then you'll end up with joules, and that's the potential energy. So what we're saying here is a half mv squared equals the potential energy. We can manipulate this, and we find that the velocity here is square root of TE voltage over m. If a potential difference is established between the two deflecting plates P and P as shown, the resulting downward electric field deflects the negatively charged electrons upwards. So you've got an electron coming through, you've got a plus plate here, so the electrons are being attracted up by the electrostatic field. Alternatively, we may impose a magnetic field directed into the plane of the figure. The field results in a downward deflection of the beam. Finally, if both E and B fields are applied simultaneously, we can adjust their relative magnitudes so that two forces cancel and the beam is undeflected. So it stays in that same position all the way through, so they're exactly balanced. The condition that must be satisfied is obtained by equating the two forces. Obviously the forces then must be equal, the upward electrostatic force and the downwards magnetic force. So we just equate them like so. So we say the electrostatic force is equal to the magnetic force here. Combine this with this equation here to eliminate the velocity vector. If we combine it with that equation there, we end up with the electric field divided by the magnetic field equals square root of 2eV over m. Finally, if we rearrange that, we end up with the mass ratios, which is what this experiment was able to give. All the quantities on the right side can be measured, so En can be determined. Note that it's not possible to measure E or M separately by this method, but only their ratio. This value today is measured to be 1.7588 times 10 to the 11 coulombs per kilogram. Thomson measured EM and found it to be a unique value that was independent of the cathode material and residual gas in the tube. So under they use lots of different gases and lots of different metals here to boil off the electrons. No matter what gases they used or what metals they used here, that always got this same mass ratio. So that proved it beyond doubt. It was a pivotal experiment, really, a very famous experiment in its day, and well, it still is a famous experiment. 15 years later, Thomson's experiment here, Millikan, another scientist, succeeded in measuring the charge of the electron with his famous oil drop experiment. So he was able to actually measure the charge on an electron. And he found that the magnitude of electron charge is 1.6022 times 10 to the minus 19. So he found what that was. And then, having this experiment already given us the electron to mass ratio, Millikan then just simply plug in the E and then find the mass. So it turns out to be 9.11 times 10 to the minus 31 kilograms. So the mass of an electron is an infinitely small value, almost beyond comprehension. It's that the mass is so small. But what's amazing is, with this experiment and Millikan's oil drop experiment, they found it to this level of accuracy. Quite incredible, really.